Hello, how are you? I'm Gary, and thanks for taking the time to watch this presentation on addressing common DSA problems in Swift, and specifically making them more Swifty. These DSA problems are often asked as part of job interviews, and I find it surprising that employers would be satisfied with just the standard learnt algorithms. In this series, we're going to take a deeper look into Swift, so that even if you're familiar with the algorithms, then you might also learn something about the Swift language and the power of its standard library. In this episode, we're going to be looking at the problem of extracting the longest palindromic string from a given string. I'm not going to explain the algorithm in great detail, but instead dive straight in with issues that I personally have with a proposed solution, specifically the programming style. These generally seem to be a simple translation from basic pseudocode to something that just runs in Swift. I also take issue with the way some of these problems are specified. In this case, it is rare to see anyone define exactly what is meant by palindromic. What's the minimum length for a palindrome? Can we have an empty string? Can we have just a single character? Are there any constraints on the string that is passed to the algorithm? Is the solution even unique? In this case, it is not. What should we be returning? The first solution? The last? Any or all of them? Sometimes it will specify just the first palindrome. But what about accented characters, Unicode, whitespace, punctuation? Am I being pedantic? Well, perhaps, but it is this level of questioning and understanding the strict constraints of a function that helps us avoid bugs found later when the code is presented with edge cases. Asking these sorts of questions demonstrates that you are a thoughtful coder. Now, to avoid upsetting any one specific code, I asked an AI to generate a solution for me. Curiously, in the space of only a few days, the same AI offered up two really rather different pieces of code. If AI is meant to be replacing us as programmers, it would do well to not only fully appreciate the language, but also to create code with some form of consistency. To illustrate the coding, I'm going to be using a Swift playground in Xcode, and I've already pasted in a given solution along with some test examples. Let's take a look. As you can see, we've got the code now pasted into a playground in Xcode, and looking through it quickly, we can see we've got a main function here called longest palindrome, into which we're going to pass a string, and it will return a string of the longest palindrome. Further down, we've got a supporting function, expand around center. This gets called twice within the main function, once when it's looking for odd length palindromes and another time when it looks for even length palindromes. I'm not going to go through the exactly how this algorithm's working at the moment, but just to say that there are those functions. And down the bottom, we've got some print statements with some example strings. We can see at the bottom of the playground down here the outputs, and well, they all look correct, so it seems to be working well. Just so I say, this expand around center is what this particular DSA solution is sometimes called. It's also an ON squared order of complexity. So there is a more efficient algorithm, but it's more complex, and I'm not going to worry about that in this particular presentation. Okay, so let's start looking at this function, and straight away I've got a problem. We've got the argument is unnamed for the longest palindrome function, and well, lazily we have this single letter for the argument, and I just don't like these single letter variables. I don't think they're terribly descriptive. There's really no reason to be using them now. Objective-C and Swift allow for named arguments, and they're a good thing. It can help the code become more readable. So I do see in a lot of examples these unnamed and in a sense underscores for all the arguments when I'm seeing DSA solutions or people offering solutions in Swift. And I think the reason they're there is because they want to make the functions all look and behave like a lot of other languages. So when we pass an argument into a function, it's not named. But that's not the Swift way. To make this, I think, better, we would replace the underscore with a word such as in. And what happens now, we can see that, well, this function doesn't work because we're missing the argument label. If I hold down the Option key, I can actually select multiple lines. And if I just put the argument in, or the argument label, okay, we're working again now. And longest palindrome in, I think, just reads better. I've also got a problem with the fact that there's just a single S here. But actually, rather than change that, I think it would be better, rather than just having this as some kind of general function into which we pass a string, it would be better if we wrapped this in an extension on string and that way we'll call it as a function on a string. So we've wrapped that in there, and we now see that well, first of all, the print statements don't work. We'll have to rework them. We don't need this argument anymore, so I'm going to get rid of that. And of course now, well, everywhere it was referencing S isn't there. We need to replace that with self. So I'll just quickly go through and we'll put self in, because that means we should be able to compile again. Okay. And well, the function's working, but of course none of these print examples are. So I now need to change this so that I call longest palindrome as a function on the string. So that works, but I need to change all of them. That's going to take a minute. You don't need me to be doing that. So I created a little code snippet, and we can see that's all working again. So that's looking nice. Just going through the function, there's some things here that I really don't like. First of all, I am concerned, why are we creating an array of characters from the string? Well, I think I know why, and it's because what we ought to be doing in Swift is interrogating the string by looking at string indexes. But they are somewhat opaque. They're not quite as straightforward in terms of how we create or manipulate them as just an integer as an index in an array. And I think what's happening here is that the whole algorithm has been translated into Swift, but they want to do the minimum amount of work possible, which basically then means we're going to have to make a copy of the string into a character array. And that's actually using extra memory. If the DSA specified that you should not be using any extra memory, well, other than local variables in the algorithm, then this line is a no-no. Then for some reason we're sort of caching the count, the size of the chars array, into n, and then we've got kind of a guard statement which says, well, if n is smaller than 1, meaning it's empty, we'll just return an empty string. Well, I'm all in favour of guard statements, but why isn't it at the top? That's where it ought to be. We don't need to be doing anything else. Of course, we don't now have n. Instead, we need to reference count on the string. And what we're going to say is, if it's smaller than 1, well, actually, we don't want if anymore. We want to guard the count. And we want the count now to be greater than 0, else we're going to return an empty string. But actually, I think we can do better than that. If the count is 1, we've just got a string with a single character in it, and that would be the result, the palindromic string. So actually, we don't really need to do the algorithm unless the count's 2 or more. But obviously we don't want to return now an empty string. If we look at the results down here on the bottom, we can see we're now missing that letter A. What we want to return in here is the string itself. And now we're back to the correct results. I'm going to get rid of this N because it's now only referenced in one other place here. And just for the time being, I'm going to change that to chars count. And we're all working again. Okay, so we're creating this value of I. Now, I know that loops traditionally, we tend to see letters like I, and then if we've got another loop within that loop, we go to J and then maybe K. But there is a historical reason for using those, and my understanding is it's because they were how you would define an integer variable in Fortran. Well, we're not in Fortran. We can call our variables whatever we want, and we can make them whatever type we want. So, yeah, I'd like to get rid of that I, but we'll just leave it there for the time being. And then further down, well, what's going on here? Well, you see the algorithm is using these two variables, start and max length. They're going to get modified by this expand around center function. And then from those variables, we're going to actually create the string start and end indexes, and we'll put them into a range, and we end up with a substring into which we then return. Now, we construct a string. Why is that, I wonder? Why do we need this? Let's get rid of it. Why don't we just return R? Oh, we've got a problem. We cannot convert the return expression of substring to the return type string. Oh, these are different objects. So when we look for the substring in a string, it's not actually now a string. It's technically a substring. Okay, well, Xcode's offering to fix this. Yeah, but if I imply that, no, we're just back to where we were. Okay, that's not really what we want. Should we be returning a string or a substring? I think we should be returning a substring. I think that's the way to go. And the problem is up here on longest palindrome. That's not a string. That should be a substring. Okay. Does that work? Well, here we were returning, if you remember, self. Well, that's not. Okay. What we actually now need to do is create a substring on self, but of the whole string. And that seems a little bit convoluted, but I am happier with that. And in fact, if we look at the print statements, yeah, everything's working okay. Let's just have a look at this idea of a substring, just to understand what's going on. So let's create a substring, and I want to create it from this particular string here. And if I open up the results from the playground, we can see, if we just scroll down to the bottom, okay, so we're printing that, but here's the substring we've created. Let's just, on that substring, ask for the first not the first index, the start index, and also the end index. And we can see that the start index is 3, the end index is 13. That seems strange given that this substring actually only has 10 characters in it. What's going on? Well, what's happening is this substring, the underlying data for it is this original string. And instead, the start and end indexes are just referencing this bit here. So what it means is, when we create a substring, we're not using more memory. And that, I would think, is a good thing. If we're going to extract a substring from a string, yeah, I think we should be returning that. Let's just have a look at the definition of a substring. And oh, this is interesting. So this is the Swift documentation on it, and it says important. Don't store substrings longer than you need them to perform a specific operation. A substring holds a reference to the entire storage of the string it comes from, not just to the portion it presents, even when there is no other reference to the original string. So okay, that's kind of what we've seen here. Storing substrings may therefore prolong the life of a string data that is no longer otherwise accessible, which can appear to be memory leakage. So what it's saying is that, yeah, it's all very well returning a substring, but potentially we could pass into this function a really big string, megabytes in size, and it's going to find a longest palindrome, which could be quite short. Well, if all we're interested in is the palindrome, we probably ought to turn that substring into a string. And we can do that just by calling string and constructing it from the substring. And we end up with now a string. But I think it's better that we do that outside of this function. So I am going to keep that as it is because I think that's the proper Swift way to do it. Okay, let's look at this expand around center. And again, we've got all these unnamed arguments being passed in. And what I particularly don't like are these underscores. Let's just hide these results. And we've got in-outs. So when we have an in-out argument, we pass that in by reference because this function is going to be modifying start and max length. I don't like in-outs. I don't like the idea of a function messing around and changing variables being passed in by reference. I think it's a source for potential bugs. I understand that we used to do this sort of thing in the past where we would pass pointers in. We've got objects being passed in by reference. But in this instance, I don't think it's very Swift-like. I don't really like it. Now, something we can do within Swift is this expand around center function. Well, it's pretty unique to the longest palindrome function. I don't think we're ever going to really want to use it outside of the longest palindrome. So Swift lets us embed functions within a function. So I can cut that out and put it in here. And yeah, it's still working. That's fine. But it does more than that, because now we've got the function embedded in this parent function. This function can capture variables defined here. Well, that means we don't now need to pass in chars, and we don't need to pass in these start and max lengths either. And just put in this left and right. Well, obviously we need to clean it up where it's being called, but let's get rid of these and see what happens. Okay, we're still running. It's still working. It's looking good so far. But we've still got a problem, and the problem is that we are working with these integers into this characters array. This characters array, that needs to go. We need to work on the string indexes. So of course now, needless to say, we're not going to be compiling. And what we want to be doing in here, I believe, is we want to loop over. Well, I'm going to make it a longer variable name, and I'm going to call it string index, and we want it to be in the range of the string's start index up to the string's end index. Oh, okay. That doesn't work. What's the problem? Protocol sequence requires that string index conform to stridable. So these indexes, which actually aren't just part of the fact that the string is a sequence, It's because string also conforms to being a collection, and they're not actually stridable. That means we can't enumerate through them. We can't create them in this range and have it incrementing. I think what we're going to need to do instead is declare string index as a variable, and we'll start it with, well, it's completed it for me. That's what I wanted. Start index. Don't actually need self. And then here we want that to be while the string index is, well, basically smaller than the end index. Okay, that's good. Except that's going to loop for a while. We now need to increment string index, and again we can't do anything like this. Okay, it's going to come back and say no, it doesn't mean that. Oh, did it mean plus equals 1? Can we do that? No, we can't use binary operators on the type of string index. They have to be manipulated by the string itself, and the reason being is that I'm going to say I want the index after the string index. Okay, that works. And this idea of the start index, end index, having index after, this is all something that needs to be implemented by a type that conforms to being a collection. And we're going to look at the differences between these protocols of sequence, collection, bidirectional collections. We're going to look at that in a later video. But for the time being, this is what we need to use. It seems a little bit more of a faff than just playing with integers, but it is the correct way to do it. And there's actually a good underlying reason to do with the way string is potentially storing its characters. So, okay, that's looking okay, but obviously we don't have I. Okay, we could pass string index in there. What is this? This is basically the left index and the right index that we want to start at when we expand around the center in the string. Well, if we think about it, first of all, we've got something else here that's just horrible. Single letter variables. Now, I know they're being used in limited scope, and yeah, I get the idea that L is for left and R is for right, but L is particularly nasty on its own because in a mono-spaced character font, such as we have here, an L and a 1 look remarkably similar. And actually that is, if we had the chars as an array, is a perfectly valid expression to ask for the character at index 1. But if we didn't mean 1 and we meant L, we could have a bug that wouldn't necessarily be that easy to spot. So I don't like single character variables, as you're finding out. So let's declare left index, and actually what it wants to be is, well, do we need to pass it in? The left one's going to be this string index that we've defined up here. So we don't actually need to pass that in at all. And the right index, well, that wants to be the string index, but it might need to be incremented. How about, you see, in this function here, essentially, we want right to be incremented by 0. And here we want it to be incremented by 1. So how about, let's get rid of these and simply have an offset. Now we can say we want the right index to be an index, that's from the string, where it is the string index, but offset by the offset. Okay, so when it's 0, it'll be offset by 0. It'll just be the same as string index. Otherwise, it'll be offset by 1. Okay. In fact, if offset by is how Swift likes to call it, how about we use offset by as well? Okay, we need to now put the missing argument label in, so we'll make that offset by, and that's looking good. Okay, right, so all we now need to do is look at this. So while L, well, that was the left index. While the left index is greater than or equal to 0, now we can't have it greater than or equal to 0. It needs to be greater than or equal to the start index. And the right index is smaller than, well, we haven't got char's count anymore. We want the right index to be smaller than the string's end index. And we want to look and see whether or not we've got two equal characters, which means we're expanding out and looking for a palindromic string. That needs to be self, and we reference it with left index and self, oops, right index. Okay, that's better. So down here, we're looking to see whether or not we've now got a left or a right index that's bigger than the current max length that we've stored. Well, first of all, if I say if right index minus left index, you see, we can't do this because if you remember, the indexes aren't stridable. We're using a function minus on stridable. The string index doesn't conform to this. In fact, there's another function we need to use, which is part of the fact that string conforms to being a collection, and that's a distance function, because string or the collection knows how to handle distances between indexes. So if the distance from the left index to the right index is greater than max length, then we step start equal to left index. Oh, actually, that's not going to work because start and max length these are integers, aren't they? This is what we're changing in order to find, in essence, what we've got happening down here. I don't think we want those. I think we would be better to start by modifying a range. And I'm going to have the longest range, and I'm going to start with it. Oh, it's offering to put that in. Start index up to, but not including start index, which means it's an empty range. Actually, I don't think it's an empty range that we want. I think it needs to be a closed range, because we're going to start with a range of value 1. Because if we don't find anything, that's the character we want to return. Although actually we've guarded for it up here. And down here, we don't actually now need to do this calculation. We can get rid of this. And instead, what we're going to return is on self the longest range. And that's what we're going to keep modifying in here. So now what we're saying is if the distance from the left index to the right index is greater than, well, it's going to be the size or the distance within the longest range. Oh, and look at this. It's actually offered to complete it for me. Distance from longest range lower bound to longest range upper bound. That's what we want. Okay, well, that's handy. Oh, and it's also offering to fill that in, which is also what we want. We want the longest range to be left index up to the right index. And actually, it's also offering here to fill in the incrementing the right index and decreasing the left index. Well, actually, that's what we want as well, although I'm not going to do it in that order. So we're going to decrease that. We don't need any of this anymore. Okay, that should now compile nicely. Oh, it does. But we've got a string index is out of bounds. Oh, how's that happened? I thought we were guarding against all of that here. And because we're in a playground, it's not actually telling us where it is. Let's show results and see what's happening. Okay, so expand around center. Okay, I'll set the longest range. And the problem is when it's calling. Oh, there it is. String index before. Well, that's this line here. We've got an index out of bounds there. Ah, I know what the problem is. The problem is that in the previous algorithm, we kept subtracting 1 from the left index, which back then was just L. And then we were checking here that L was greater than or equal to 0. And if it wasn't, well, we'd bail out, which was fine. But actually, we've got a problem because string is not going to allow us to create an index before the start index. In fact, that should say start index and not string index. But that's not why we've got the index out of bounds. Yeah, I think what we need to do here is we need to guard that the left index is greater than the start index. Else, well, we'll just break out of the loop. Oh, and it's working again. Well, that's good. Actually, we don't need that in there at all for it to work. Yeah. But the right index is okay because the end index value is the end index beyond the string. It allows me to increment right index up to the end index, but I can't have the left index being decreased to a -1 or a value before the start index. Okay, well, I think we're pretty much working. Oh, this is looking good. That's, in my view, a proper way to turn this algorithm into something that works properly with Swift strings, and looking at Swift strings by their indexes. Okay, I think I'm happy with that. Although, maybe there's one more thing. If you remember, I did say that all of this index stuff is here because string conforms to being a collection. So what happens if I change this extension from a string to a collection? Well, now we cannot convert expression of type, what does it say? Self subsequence to return type substring. Oh, of course, because it could be anything. We're not now going to be returning a substring. We need to change that to self subsequence. We're now working with extending the protocol rather than string. And we've got generics involved. Oh, we're still not compiling. Why aren't we compiling? Let's have a look. Reference operator equal on equatable requires that self element conform to equatable. So we can't just do this on a collection. It needs to be on a collection where the element conforms to equatable. Oh yeah, and that now compiles. Oh, okay, we've got another problem. Incorrect argument label in call have before we expected after. Oh, replace before with after. Well, we don't want to do that. We want the index before. The reason for this is that this doesn't work just on a collection. We need to be able to enumerate the indexes not just going forward by using after, but we also need to be able to call an index before. And that doesn't work on a collection. It works on something called a bidirectional collection. So, for example, if we had a linked list, and we might look at that later, we could have a linked list conforming to collection because that would enumerate forward. But a linked list, a one-directional linked list, wouldn't conform to bidirectional collection. So, but string conforms to bidirectional collection. And now we've written a routine that is actually not just working with a string. This would look for a longest palindromic sequence or subsequence in any bidirectional collection where the elements are equatable. Now, I wonder if I can think of one. How about an array of integers? Okay, let's create that. Oh, it's offering to do that. Thanks very much. I think I'm going to make you a bit longer. Okay. Now, let's say palindrome of array, let's call it, equals, on the int array, I want to, can I call longest palindrome? Yeah, apparently I can. What's it saying it looks like? Well, that seems to, yeah, that's working. Let's put it in a print statement. Yeah, wow, that's pretty powerful. Yeah, I like it. I wonder if we can do something else. What about data? Data's bidirectional, and that's made up of bytes. They conform to being equatable. Okay. Let's see. I've got a code snippet here. Okay. Doesn't find data in scope. Yeah, so data is not part of the standard library. We need to import foundation. Let's have a look. Oh, now that is interesting. So we've now converted that int array into a bunch of data. And if we have a look at it, oh, that data's got 80 bytes in it. And then when I look at the palindrome, it's got 71 bytes. That's sort of interesting. It's got an awful lot of zeros in here. That's because this integer array is, each integer is actually 8 bytes. That's 64-bit. Let's make that a uint8 array instead. Okay. Okay. That's sort of what I was expecting. What we've got here is we're now calling longest palindrome on this integer array, but these are in fact just integers that can unsigned 8-bit. And that's the first one, is the palindrome we're getting. What we then do is we're going to take that integer array and we're going to create a data buffer from it. And on the data buffer, we're calling longest palindrome. From that palindrome data, we're going to turn it back into an array of unsigned 8-bit integers. and that's what we've got here, a decoded uint8 array, and when I print it out, well, we're seeing the same array. It's just that we converted it to data and called longest palindrome on data. This is now a very versatile function because it'll work on, as we were saying, any bidirectional collection where the elements are equatable. And that's the power of Swift. And this is the sort of thing that I'm just not seeing in DSA solutions. And I think it makes it more worth the effort of faffing around then with the collection's indexes. So that's it for this episode. I hope you found it interesting and maybe you learnt something about Swift. If you did, please leave a comment below and remember to click the like button, subscribe and get notifications about new videos. Apparently it helps the algorithm, whatever one of those is. Anyway, until next time, goodbye.